Good morning, friends. My name is Ashutosh Garg. I work as a solution provider with Furnace Improvements. Our company completed 25 years in fired heaters business in the US. We have been conducting free fired heater training webinars this year as a part of our Silver Jubilee celebrations. Welcome to our second training session on refinery fired heaters. We have a full house, more than 140 people have registered today, and I thank all of you for your time and interest. We are going to be having interactive presentation for 90 minutes. Please keep on sending your questions on the GoToWebinar platform. We had conducted session 1 on refinery fired heaters in April this year. All our previous webinars are available on the YouTube channel and also on the GoToWebinar. So this webinar is different from the webinars you must have attended before. We will be conducting this webinar through Kahoot. It's a game-based learning platform that makes learning very easy. So here is my request to all of you to get the full experience. Please download their app or go to www.kahoot.it. The pin is already there, 1277333. So I want all of you to log in, and I want to assure you your identity is completely anonymous. Nobody will be knowing about your identity. We have put the game setting in such a way so that even I don't know who is there. So let's try to get the game started, and we will hope all of you can log on to my platform on Kahoot, and let us start this presentation today. So welcome to our interactive training webinar on refinery fired heaters. We have been doing this training for more than 20 years now, doing training of engineers, doing training of operators, and I learned doing these webinars last year when there was pandemic. So as I said, we would like for you to log on to Kahoot, and the pin is 1277333. So let's begin our presentation this morning. Let's keep it very informal. So if you have any questions, please send it to them. Send it to the GoToWebinar through the questions box. You can send it, and we will try to answer them today, or if not today, in our next webinar. So we want to find out from you, if you are managing a fired heater, if you are operating a fired heater, what is the heat duty of your fired heater? And we are asking you to put it in million BTUs per hour. What is the duty of a fired heater? You may be managing more heaters. So we have a few answers here. Some people are saying they have a heater between 150 to 250 million BTUs. Some are telling us 50 to 150 million BTUs. So just to let you know, the average size of fired heater in the US is about 78 million BTU for natural draft fired heaters and 120 million BTUs for a balanced draft fired heater. Fired heaters is a very unique equipment. You all know that. Almost 40 to 70% of the total energy in the refining industry is consumed by fired heaters. It's basically a high temperature heat exchanger. wherever heat exchanger cannot be used, we use fired heaters. So we'll talk about more on fired heaters. In fact, for the next 90 minutes, we'll be talking about fired heaters. So I want to ask you, when was the first oil refinery built in the world? Hey, I really like your response. Almost everybody got it right. The first refinery in the world was built in Romania in 1856. They had plenty of oil available at that time. In the US, the first oil was drilled around 1858 in Canada, or rather in North America, and the refinery was built around 1860. And the industry grew slowly in the beginning, but then it kind of, in the 20th century, uh, it took off because of the introduction of the automobiles. Well, thank you for the answers. Let's move on. Please don't worry about the scores. Those are kind of built in, so we need to remove them. So I want to start the session today with a brief introduction of myself. I'm a chemical engineer from IIT Kanpur. I passed out in 1974. And since 1976, I've been working on fired heaters and combustion systems. I worked with KT India, Engineers India, and KTI Corporation in the US. Since March 1996, I've been working with furnace improvements, fixing heaters for the past 25 years. And I want to tell you a little bit about furnace improvements. Furnace improvements is paying for this webinar, pays our salary, all the things. So we have to give it a couple of minutes before we resume our session. We started furnace improvements in 1996. We have 3 offices. We have a main office in Sugarland. The engineering office is in Noida, India. We opened up in 2005. And then we opened a CFD modeling office in 2014. And our focus has been on revamping fired heaters, improving their efficiency, increasing their capacity, improving the run length, reducing NOx emissions. So that's what we have been doing for almost 25 years. We have 3 patents on improving the performance of fired heaters. We have a team of 30 engineers in Noida, India for doing all the engineering work. And we have a team of 4 people in the Pune office, and they do the CFD of combustions, heat transfer, fluid flows. I think we are the only heater company with its own CFD modeling. We take pride in doing high quality technical work. Because of the time difference, we are practically working around the clock. We are very focused, we are very small, so we are able to keep schedules. And our philosophy is do it once, do it right. So we think that is the most efficient way of doing business or fixing heaters. So just do it once, do it right. I also want to thank our team of engineers, especially process people, and especially my colleague Deepika. She has worked very hard for the past 3 weeks on putting this presentation together. They have done all the hard work. I am just the front face. They asked me to present it. So they have done an excellent job of putting this presentation, putting it on Kahoot, and even writing the script for me. So basically, thank you, team. So In our first session, we covered fired heaters. We talked about typical problems in fired heaters. One of the things we had asked all our participants in the first session was to give us 3 problems in fired heaters, what they are experiencing, and we had almost 300 to 400 bullet points to cover in our future seminars. We also covered fired heater nomenclature, different types of fired heaters, and that's what we covered in our first session. The session is available on YouTube. If you have not watched it, please go and watch it and give us your suggestions. We want to improve it even further. So today, we will be covering 3 major components of fired heaters. We will be covering radiant section, we will be covering convection section, we will be covering stack, we will talk about design considerations, we will talk about major issues, how you can improve capacity and efficiency by convection section revamps, talk about draft control, and also we will talk a little bit about API 560. Those of you who are not familiar with API 560, it is a API stands for American Petroleum Institute, and 560 is the standard for refinery fired heaters. So we will talk about the changes which have taken place in the last couple of months. We want to tell you, bring you up to speed. We will talk about those things as well. So here is a question for you. What percentage of heat is absorbed in the radiant section of a refinery heater? Uh, so there is a 50-50 split between 60% and 70%. For refinery fired heaters, 70% appears to be a better estimate than 60%. It is not that the 60% is wrong, but most of the heaters, what we see, have 70% heat transfer. And if you have air preheating system, then it is even higher than 70%. You could be going up to all the way up to 75%. So radiant section is the biggest section where the heat transfer takes place. So most of the work is done in the radiant sections. So let us talk about how the fired heaters came about. As we talked about, fired heaters were developed in 1800s, in the 19th century. And initially, the fired heaters used to be the batch process. They were like shell stills, and they would have several stills right next to each other. And as they would coke up, they will shut down a few, clean it up, and then again bring it back online. So that was the system when the refineries initially started. And then it turned out that we came to something which is known as pipe stills. Instead of the shell stills, heating the oil in a shell, in a cylindrical vessel, we started heating a pipe in the pipes. So that's why the name pipe stills came up. And what I want to tell you is, in these heaters, there was no radiant section. They were all based on convective heat transfer. So what we had was a combustion chamber. If you see the shell still over here, they are from refinery operations by Bill Berger, their courtesy. If you see, it's almost like an oil-fired or gas-fired boiler, and they would have plenty of those shell stills like these, where they will be having it. And then when they came up with the pipe stills, even the pipe stills did not have any surface in the radiant section. They were all based on the convective heat transfer. In fact, the convective heat transfer, they used to have so much heat transfer taking place in these few rows that they would start coking up. So then they came up with a design where they started recirculating flue gases to lower the temperature and lower the heat transfer rates in the shield tubes or in the convection section. But and later, around I would say 1940s or maybe around 30s, 40s, I don't know the exact time, when we came up with the concept of radiant heat transfer or started putting heat transfer surface in the radiant section. I can show you several configurations which were built historically, and we have to give credit to two very talented engineers, Walter Lobo and Evans, who in 1939 did this wonderful research and came up with the Lobo-Evans correlations for designing fired heaters. Those correlations are still used by all the fired heater companies. That is how good their work is. So courtesy Lobo-Evans, that's why we have radiant sections. And here you can see all sorts of heaters which were built. Historically, all heaters used to have horizontal tubes. And you can see those over here. They always used to have horizontal tubes. And then around I would say 1950s, the concept of vertical tube or vertical cylindrical heaters was introduced. In the beginning, okay, no, it's, yeah. Sorry. In the beginning, they would have two rows of tubes. I will cover this. Let's answer this. What type of problems you are having in radiant sections? Because most of the problems which we hear from our clients are in the radiant section. Most of the problems in the heaters are taking place in radiant section, and we have the results. You can see people have coking problems. People have flame impingement. Some have short tube life. And most of the problems are high tube metal temperature. So we will talk about all these problems a little later. But this gives you an idea about the heaters, what type of problems we are having and how to fix them. That's what our job is, fixing problems. So radiant section, as we said, is the biggest component of fired heater. And here the heat is transferred by radiation to the tubes. Most of the tube failures also occur in radiant section due to high tube metal temperatures. It's very important we have a good design of the radiant section. Now, radiant heat transfer takes place by electromagnetic waves. Also, radiation heat transfer travels in straight line. there is a very famous equation, I think all of you know it, Stephen-Boltzmann equation. It says the heat transfer, radiation heat transfer, is proportional to the absolute temperature raised to the power 4. So that's basically the radiant section. Let's talk about what are their components in the radiant section. The most important component are the radiant tubes. We are showing you two configurations, horizontal configuration and a vertical configuration. These tubes are supported by tube supports, and we have horizontal tube supports, and then we have vertical tube supports on the top. The firebox again comprises of three components, basically the burners, the casing, and the refractory. The tubes are connected by return bends, 180-degree return bends on both the ends to connect the tubes. That's what we are showing you over here. Now, some heaters have bridge walls or gravity wall, as we call it, in the center to convert it into two zones. And the roof of the radiant section is known as arch. And the burners are on the bottom. Now, I want to tell you bottom fired burners is also 70 years old. When the heaters were started, heaters were designed in 19th century or early 20th century. Everything used to be horizontal firing. The burners would always be located on the end walls. That's typically how the design of radiant section was. So now I want to show you the modern configurations of radiant sections. The first one is vertical cylindrical configuration, very, very common, and has been very popular in the last 60, 70 years. Then we have a horizontal tube cabin furnace, and the other one is horizontal tube box. The only difference between the two is the roof, the design of the roof. And cabin, if you have a sloping roof, we call it a log cabin or a horizontal tube cabin. That is the configuration we use for many heaters. These are these are all very popular configurations. For larger capacities, we combine the radiant sections, and you can see we have got two radiant sections and common convection section. So that is another configuration we have used. I will talk about double fired a little bit later, but yeah, you can see in this heater, we are putting the tubes in the center and burners on both sides. This is another configuration which is used for small capacity heaters like helical coil heaters. Helical coils for hot oil service is very, very common. Sometimes we put a convection section, sometimes we don't even put a convection section, and then it becomes like an all radiant heater. And then the arbor coil heater. This is used for catalytic reforming services. This has a lot of, this is used for where we have to process very large quantity of gases, like in a catalytic reforming unit. So what we have is we have a number of parallel passes. These heaters are categorized by low pressure drop or characterized by low pressure drop across the radiant coil. So there is only about 2 or 3 psi pressure drop over here. And there are large headers. We can also make it the other way, like a U. So some people make it like a U and burners on the end walls, or this is bottom fired. So there are several different configurations over here. And these are all different radiant coils designs, but if one thing which you will see over here is the convection section remains the same. Whether it, whatever, depending on, it does not depend on what type of firebox you have, but if you look at the convection section, it is design is always the same design. So we will cover that also in a little bit. So here is a question for you. Why do we need spacing between the radiant tubes? I don't know if you have seen the boilers. Boilers, the tubes are right next to each other. So I want people to type the answers over here. Looks like nobody is typing. Oh, we have some answers. Okay, good. So I think these are really, really good points. Expansion, definitely, we want to take care of the expansion of the tube. So that is one. The most important is re-radiation. Have re-radiation to the back of the tubes. Better flux distribution. Generally, in boilers, we are heating water, and water is an excellent conductor of heat, and water never cokes up. So we are able to put the tubes right next to each other. In fact, we make a combustion chamber by putting the tubes and then welding them together. So it's very, very important that we put these tubes and keep a spacing. What we have found out is the 2 diameter spacing is the most optimum spacing for these tubes. So most of the radiant sections will have tubes at 2D spacing. That's typically how, and they are kept about 1.5 diameters from the refractory wall. That is also by hit and trial, the industry came to an understanding that 1.5 diameters is the most optimum spacing for the radiant tube. So that's basically the reason we provide this gap, Well, let's move on. I think so. There are 2 configurations of tubes. We have single fired, which is a very, very common design. And here we have the refractory at the back, then we have tubes, and then we have the flame. And in the double fired, we have tubes in the center and flames on both the sides. So when you are heating from both the sides, you get very uniform heat flux and lower tube metal temperatures. And that way you can use higher average radiant flux. This technology is used in a lot of critical heaters like ethylene crackers, steam methane reformers, hydrocracker heaters, in several hydrotreater heaters, wherever the flux or TMT is this thing, even in coker heaters. Coker heaters also, we use double fire designs, especially the new ones, to minimize the residence time and use a quick heating. So these are all these advantages. Now the disadvantage is when you have a double fired, the box becomes much bigger, so the cost goes up. So you always have to choose between single fired and double fired. So this is a trick question. What is the percentage of heat transfer by reradiation in the radiant section? So we have three types of radiation. We have the direct radiation, which is taking place. And this also comprises of radiation from flame and radiation from hot flue gases. Most of the radiation which is taking place in the radiant section is by triatomic gases, carbon dioxide and water vapor molecule. That's what is transferring the heat. Uh, so, and then about 12% of the heat transfer is by re-radiation. And also, now that we are talking about in the radiant section, about 15% of the heat is transferred by convection actually. So we have the convection section, the movement of flue gases also transferring heat to the tube. So basically, direct radiation, re-radiation, and convection section, these are the three major modes of heat transfer in a radiant section. So basically, that's what we are showing over here. Direct radiation coming in this thing, then re-radiation from the refractory wall, and then the convection. So these are all the heat transfer taking place, and this heat transfer takes place to the outside of the tube, and then the heat goes up from the outside to the inside, and that is also very important. And that is why the tube metal temperature comes into the picture. If we have coking inside or if we are scaling on the outside, we could be having high tube metal temperature and inefficient heat transfer. That is why the tube metal temperature is most important. And then the heat to the fluid is transferred by convection. That's typically how the convection heat transfer takes place inside whatever oil or gas we are flowing will be taking place. So Firebox has three functions, major functions. Uniform heat distribution. You want all the tubes to be heated uniformly. It is easier said than done, and that is why we have so many problems in the fired heaters today. No flame impingement. So that is also one of the important parameters, complete combustion. And some of these last two things have been amplified because of the use of low NOx burners. Whenever we use low NOx burners, our flames become very, very long. And once the flames become very, very long, we had flame impingement problems and incomplete combustion taking place. So after combustion started taking place in the convection section. So to some extent, ultra low NOx burners can be responsible for at least two of the three problems in the fired heaters. So how can we have uniform heat transfer? One way is use minimum number of fluid passes, use more burners, optimum H by D or H by W ratio, that means height to width ratio or height to diameter ratio. Have good combustion, you control the draft, control the excess O2, and also you do routine firebox inspection. So these are the operating, the last two are kind of operating. The first three are basically the design, and the last three I can say is by operating. So these are the two ways of achieving good design, good operation for uniform heat transfer is what we want to achieve. So when we are designing fired heaters, there are several ways to design it. And one of the, if you want to achieve uniform heat transfer, is to not make it very tall and narrow. I don't have to explain this, but anytime you make tall and narrow heater, you will have a lot of heat transfer in the bottom and very little heat transfer in the top. So the ratio is considered 2.5 for the VC, and similarly for the cabin heaters. What are we gaining? If we make a wider firebox, we get uniform heat transfer. What are we losing? It becomes a little bit more costly. We need more area, as well as it becomes a little bit more expensive. So you have to kind of decide where you want to be. So one of the problems what we have seen in cabin heaters is pass imbalancing, and what we have seen in that the two passes on the top are running very cold and the two passes in the bottom are running very hot. So that happens pretty often. And what we feel is if you have that type of problem, there are many ways of solving it, but one arrangement is called nesting of the passes. So the two passes, they travel together. If you can see in the third over here, basically the passes are traveling together, and that kind of ensures uniform heat transfer or uniform heating of passes, that all the four passes will be uniformly heated. So that is one way of solving if you have a non-uniform heating or pass imbalance, to reconfigure the coil like this design. So here is a question for you. What is the typical average radiant heat flux in a boiler? Why don't we take a guess? Well, let us see what, I think people are still typing it out. All right. The typical average radiant, these answers are good for fired heaters, but in boilers, we go anywhere between 40,000 to 80,000 BTUs per hour plus foot square. That is how high flux we go in the boilers. And why do we go that? Because we know it's not going to coke. And also we know water is an excellent heat transfer conductor. So because of that, the fluxes are very, very high. But in fired heaters, we are processing hydrocarbons, and hydrocarbons can coke or crack. So all those type of things kind of limit us to around 10,000 BTUs per hour foot square. And those of you who do not know what the flux is the heat duty per unit area, like in terms of BTU per hour plus foot square, or kilocalories per hour plus meter square, and why do we limit it? Because we have a restriction on film temperature, coking, and run length. You don't want to be decoking your heater every year because it's going to, you will have to shut it down and for 3, 4, 5 days, and you will have a lot of production loss. So the general guidance is lower radiant heat flux is better for you. So these are the reader's questions. These questions we have compiled from our participants, and you can see most of them are talking about how to increase the run length, how to increase the tube life, how to eliminate hotspots, how to prevent flame impingement, how to reduce TMTs. So as I see, there are lots and lots of issues on gradient section operation or design, and it can make a big difference in the having a successful heater or a problem heater. So as we said, high tube metal temperatures is a very common issue in fired heaters, flame impingement, overfiring. Low flows can lead to coke buildup, and typically 1/8 of an inch of a coke can add up to about 100 degrees of TMT. So that is how fast TMT can go up when you have coke formation. So one of the secrets, I should say, of having a good fired heater is keep your flames away from the tubes. As we learned in the very beginning, the radiant heat transfer does not need a medium. So it travels in straight line, and Stephen-Boltzmann equation, it's basically proportional to the absolute temperature raised to the power 4. So the burner to tube clearance is a very, very important parameter. If you have a lower clearance, you will have a much higher chance of flame impingement. And this has been aggravated with the ultra low NOx burners. I want to tell you, when Lobo and Evans were doing research in 1939, the burners used to be all premix burners. Just the type of burners what you have in your home, gas burners. And the flames used to be very, very short. So they made an assumption of uniform heat transfer, or CSTR model, continuous stirred tank reactor model actually. Now, audio? Hello? So if so API 560 standard has been providing minimum burner to tube clearances, and those are followed. But in my opinion, they are not enough. You need to be going higher than what API 560 provides. So we have developed a technology called inclined firing technology, and it is very, very simple. We are putting the burners at an angle to keep the flames away from the tubes. We put burners at about 6 to 7 degree angle. And by doing this, as you can see in this picture, the burner flames move away from the tubes. And we have seen temperature reductions of anywhere between 100 to 200 degrees F. It's a very, very simple technology, and it is especially suited for low NOx and ultra low NOx burners, and it takes care of the high tube metal temperatures, which is the biggest problem in fire heater. So if you have any issues on high tube metal temperatures, we can always evaluate your heater and recommend you inclined firing technology. Very, very simple technology and very, very good. I think it should be used in all vertical cylindrical fired heaters, definitely, if not all. And as you can see, all we are doing is putting these burners at an angle. And we can use existing burners, we can use new burners, and we can incline the floor or we can use the same floor. But that's all what we are doing. We are not. And by doing this is very important. For every 10 foot of flame length, we get another extra foot of clearance. So if you got a 15-foot flame length, the flames move away by 1.5 feet. And this is very, very important, especially in old, tight heaters. That's what we. This is an example showing for a 8-burner system, when we put it at 7 degree, how the clearance goes up from 6 feet to 9 feet by about 25 foot. We assume the flame is about 25 foot. This was a 65-foot box, vertical cylindrical crude heater at one of the Texas refineries. And you can see how we are able to deflect the flames away from the tube. And this does not affect any heat transfer. That's a good news. That your heat transfer still remains the same, as I said. So here is a question for you. What happens when the tubes coke up? Are you all able to hear me? I think I'm really impressed. Most of you have really, really covered the TMT issue, the pressure drop issue, the overheating, tube rupture, reduction in heat transfer. So thank you all for contributing. Very, very, very good answers. And my slide also shows the same, so there is nothing more to add. Tube metal temperature goes up, pressure drop goes up, firing rate goes up, firebox temperature also goes up, that's efficiency goes down, throughput starts limiting, and ultimately you have to shut down the heater and clean it. So coking is something you don't want to have coking in your heaters actually. And this is showing a tube metal temperature profile for a clean tube and a foul tube, and you can see clean tube is around 950 and coke is adding another 200 degrees, so the metal temperature has gone up to 1150, just by eighth of an inch of a coke or quarter inch of a coke can go that, So we looked at so many heaters. We looked at so many crude heaters, vacuum heaters, uh, coking heaters, coker heaters, and we kind of developed a coking index, because so far all the heaters what we talk about don't talk about the coking tendency. So when you're buying a heater, you don't see how fast it's going to coke up. So we looked at and we said, what are the parameters you need to be focusing on, especially if you are buying a heater? If you are buying a heater, what are you looking at? You are looking at average radiant heat flux, mass velocity, coil inside diameter, burner heat release, burner to tube distance, and burner air side pressure drop. And basically, these 6 parameters can tell you, even before you're buying a heater, whether it is going to be coking or not, or how fast it will be coking compared to the relative other designs. So we are still looking at it, but if you have a heater, you're having coking issues, you can send it to us. We can evaluate and tell you what will be the coking index for this heater and how you can reduce the coking. We have designed heaters where we have designed them for 8 years run length of crude and vacuum heaters. We did it for a refinery in Lake Charles. So, and it kind of worked for 8 years. So basically, the coking has never been talked about during the design. Uh, Most of the people make sure that whatever the licensor has specified is taken care, whatever the engineering company has specified is taken care, or whatever is the API specifies is taken care, but they don't talk about, hey, is it going to coke in 2 years or is it going to coke in 6 years? And that's where I think you need to be, as a buyer, as a specifier, you need to be looking at some of these parameters to see, am I buying a heater which will coke in 2 years? Will I look good? That's what we can't kind of thing. So I have these 3 designs of a heater, crude heater. Actually, this is a real situation. And we designed it using 3 different H/D ratios. And they all meet API. So if you look at this heater, this one has a coking index of 13 and this one has a coking index of 26. What it means is this heater will coke at twice the rate. If it's 26, this will be coking. If this cokes in 3 years, this will coke in 18 months. Or if this cokes in 4 years, this will coke in 2 years. Now, the question is, if you look at the cost, anyway, you are paying a little bit extra for the heater. But if you look at the cost, one shutdown will cover more than the difference between what you are saving. So look at the long run and see if you are buying a reliable heater or not, actually. And coking index can tell you, even before you operate the heater, how good this heater is going to be. So that was our coverage on the radiant section. We will cover the convection section now. So we have a small quiz for you. Convective heat transfer takes place by I think we got most of you got correct. Bulk movement of molecules. That's the convection. The velocity of gases is basically what is transferring the heat in the convection section. So the shield section is the section which is at the inlet of the convection section. And it's also known as shock section. That's where the maximum heat flux or maximum heat transfer rate is experienced. And it's basically where both radiation and convection heat transfer is taking place. So it's a very, very critical section, and a lot of times it has high tube metal temperatures, it may have coking, it may have tube ruptures. It happens pretty, you know. So the function of convection section, is recovering heat from flue gases and improving the efficiency of the fired heater. And we are able to recover almost 20 to 30% of the total heat duty in the convection section. You know, that's how important the convection section is. This picture shows the convection section on top of a radiant section. So basically that's how the convection section looks. Convection section has two major sections. We call it the shield section. The bottom 3 rows or 2 rows sometimes are called shield section. And then we have the extended surface, shield section of bare rows, no fins or studs, and extended surface section are basically studded or finned rows above the bare tubes, and that's where the heat transfer is taking place. There have been a lot of improvements in the convection section, and the biggest is we can do the modularization of convection sections, and that has been possible because of the use of fin tubes or studded tubes. They basically made the convection sections very compact, and once the convection sections became very compact, we could make them in the shop and their costs came down, and once the cost came down, we were able to transport them and then install it almost like a Lego, one on the top of another. So that's basically how the convection sections are fabricated. It's basically showing you the casing, refractory tubes, intermediate tube supports, header boxes on both sides where the return bends are housed. So that's typically the layout of a convection section. So as I said, they all used to be bare tubes. And then we started with studded tubes. Studded tubes are mostly used for oil firing. But now everybody has changed over to gas firing. So fin tubes are used in most of the convection sections. So again, a small quiz for you. Convective heat transfer goes up with higher flue gas velocity, lower flue gas velocity has no effect. All right, so most of you got it correct. Higher flue gas velocity means higher heat transfer rate or higher convective heat transfer. So this is basically showing you the convection section layout. This is the radiant section over here, shield section here, convection section, extended surface tubes over here. In the convection section, 85% heat is transferred by generally by convective, and about 15% heat is transferred by radiation means. So there is a radiation heat transfer occurring in the convection section also, just like convective heat transfers are occurring in the radiant section. These are the recommended flue gas mass velocities in the convection section. Natural draft 0.3 to 0.6, induced draft 0.5 to 1. That's typically the mass velocities. So which side controls the heat transfer in the convection section? Hey, most of you got it right actually. Flue gas. Flue gas controls the heat transfer in the fired heater, I should say, not just in the radiant section, not just in the convection section, but in the complete fired heater. So it's a flue gas side which is controlling the heat transfer in fired heaters. Just remember that. So that is why uh, when we have the fins, we can increase the outside surface area by anywhere between 8 to 12 times. And one fin tube typically replaces about 3 bare tubes. So that's generally what we kind of saying. So here is another poll. I think my team wants to have an interactive, session. So generally, the radiant heat transfer is not efficient once the flue gas temperature drops below 1400. So most of the time you will see the flue gas temperature entering the convection section is more than 1400. It could be 1500, 1600. Now, when you measure the flue gas temperature, you may be much lower actually, but that's typically 1400 to 1600 is typically the flue gas temperature in the radiant fired heaters, or sorry, refinery fired heaters. That's typically. So now we talk about flue gas temperature leaving the convection section. It enters at all right, so it appears that most of you have very efficient fired heaters in the range of 400 to 600 degree stack temperature. I think once those who have less than 400 may be having an air beading system. If you have more than 800, then you need a better convection section. I'm just saying, what looks like generally you want to keep it between 400 to 600 degrees. So typical flue gas temperature, 1400 to 600, 1600 degrees. Outlet temperature, this is actually from air preheating systems. This is not, but if you know what approach is, flue gas temperature approach between the fluid inlet temperature and the flue gas temperature, these days we can go down to as low as 25 degree F. That's typically how low we can go down. So I do have a quick couple of case studies, and the reason I want to put it is you cannot upgrade the radiant section. Once the radiant section is built, it is not possible to upgrade it, but you can always change the convection section. You can always put more area in the convection section. And here is what we want to show it to you. This is a case, an actual project where the client had a crude heater and they were limited on the charge to about 68,000 barrels per day. And the heater was air limited. I mean, they were not able to push more combustion air into the heater. We came up with a recommendation to put a new convection section, new offtake ducts, and new stack, a larger stack. We did that. And when we did that, we were able to improve the efficiency from 83% to 90%, 7% improvement in the efficiency. Flue gas temperature almost dropped down by about 250 degrees. And the biggest thing was that we doubled the width of the convection section. So once we doubled the width, the convection section losses went down and they were able to fire to their heart's content. In fact, the refinery has been very, very happy after we did this revamp for them. So convection section should not be overlooked because that's where you can add more surface very economically. That's why the reason I'm kind of talking about here. Similarly, this is another case study. These are two crude heaters for a refinery in Texas. And here also we improved the efficiency from 76% to 87%. And we always tell our clients, don't just replace the convection section, always improve it. Always upgrade it. Just like for your computer, when you're replacing the graphic card, you want to go with a better graphic card, or if you're replacing the memory, you want to go with a higher memory. Similarly, for the convection section, you can easily upgrade your convection section. So this is basically, you can see, this was the convection section what they had before, and this is the convection section what we put upgraded. And we can reduce the flue gas temperature by almost 350 degrees. So there is a lot of possibilities in the convection section, and that's what we want to focus in this presentation today. The last thing on convection sections is acid dew point corrosion. That's also common, especially in air preheaters or economizers, not too many in the boiler feed water. The thing is, you need to keep the inlet temperature above the dew point, and flue gas temperature should be at least 75 degrees above the dew point. So that's typically how you can ensure that there is no corrosion in the convection section. So let's move to the last section, and that is the stack. What is a typical stack height from grade of your fired heaters? Let's see how tall is your stack. Uh, so we have it all over the range actually. I mean, there are people who have very, very tall stack, almost like maybe 250 feet or 80 meters. 200 feet is very tall. So in the past 50 years, the stack heights have really, really gone up, and that is because of the pollution. So this is just showing you the 4 different types of drafts in fired heaters. This is natural draft, forced draft. Induced draft is one where we put an ID fan to take care of the draft losses. And then this is balanced draft with an air preheating system. So these are the 4 types of drafts we use in our refineries. So what is the function of stack in a fired heater? Well, you got it right. There are 2 right answers. Safe disposal of hazardous pollutants and to maintain negative draft in this thing. It's very important these days that the ground level concentration of pollutants like SO2, SO3, NOx, CO, particulates, soot-borne particulates is kept within the allowable range to ensure safety and health of all our people, the operating personnel. So safe disposable and maintaining negative draft. That's very, very important. So stack is a vertical duct. We basically use it for creating draft and disposing flue gases. There are 3 or 4 configurations of stacks: top mounted or grade mounted, as you can see over here, top mounted, common stack, self-supported, or straight. Stack can be straight, conical, or telescopic. So we will show over here. You can see convection mounted stacks. This is a common stack, and this is a heater where we revamped and put external support. So that's another configuration for stacks. So these are different configurations for stacks. So the question is, what is draft? Because fired heaters are the only equipment in the refinery where you have negative draft or negative pressure inside the furnace. So let's see what is the answer here. Difference between atmospheric pressure and pressure existing at the furnace. Almost everybody got it correct. Thank you very much for your participation. So what is happening is we have got hot flue gases inside the stack and cold ambient air outside the stack. So because of the density difference, we create a current or negative pressure inside the stack, and that kind of leads for the supply of combustion air. Basically, it creates. Why do we keep negative pressure? And negative pressure is because you want to have inherently safe fired heater. You don't want at any time the flue gases to be coming out when you open the PEEP doors or you're going there for any reason. So you want to have a very, very safe equipment because all process equipments are designed inherently safe. This is not the case with the boilers. I don't know if you have noticed, boilers does not have any PEEP doors which you can open. So this is the difference between the boilers and fired heaters. What are the reasons for draft fluctuation in fired heaters? Uh, yes, so because of ambient temperature and because of the heater load, the draft fluctuates. So we have to make sure that. So where is the highest pressure in a fired heater? Is it here? Is it here? Is it here? Or is it here? Where exactly is the highest pressure? Highest negative pressure in the furnace. So most of you got it right. The arch, the roof of the radiant section has the highest pressure or lowest negative pressure. And that's how the heaters are designed to keep 0.1 inch arch pressure in almost all the fired heaters. So that's typically how we are controlling draft around 0.1 to 0.25 inch. Every 10 foot of bauxite gives you about 0.1 inch draft. Now, stack dampers don't have been misunderstood. Very few dampers operate correctly, and they are left fully open in most of the refineries. That's what we see, that they are left open. So there is a lot of room for improvement in the stacks. And another thing which has happened is because of the pollution reasons, the stacks have become very, very tall. And once you make a stack tall, you have to make it bigger for structural stability. So once you make it the stack diameter and height, it just goes up. And once it goes up, if you put a stack damper in those stacks, those stack dampers are highly, highly oversized. It's like putting a full size control valve in a pipe. So that's basically where the stack damper starts failing. They may be good, but if they are oversized, then they fail to control the draft. And we have seen lots of fired heaters with very, very high draft. And high draft, what it does is it leads to lots of tramp air, and it also makes the burner controls ineffective. So the excess air goes up, all those type of problems, this thing. So here basically what we are showing is this is the stack effect, which is typically common, but the pressure drop keeps on going down as the heater load goes up. So the pressure drop across the damper keeps on increasing. We design here, but it keeps on going up. So we have to have a real effective control valve for the stack damper to work. And that's another thing. What we are showing is we are showing that draft availability between day and night. I mean, I'm giving an extreme example of day temperature of 85 and night temperature of 30, but you can see how the draft availability changes. It's almost like 0.1 inch extra draft changes. So every 12 hours, the draft is changing. So your stack damper needs to control or work with the ambient temperature at all the times. So this is a stack damper which has been historically used, manual winch and cable arrangement. And sometimes I wonder your heater is costing maybe $5 million, $10 million, and we still are living in Stone Age trying to control the draft manually, using a cable and winch. So I think these are outdated designs, and for a stack damper, which is such an important component of a fire heater, especially for operation, we need a better control. And that's where pneumatic dampers come in. And we can have parallel dampers or we can have opposed plate dampers. So either of the two we can go for. So we did this study for a coker heater. And what we found is the stack was very, very tall, 150-foot tall stack, and the diameter was almost like 14 feet. And the flue gas velocity is 7 feet per second in the stack damper. And stack damper, if you want the stack damper to work, the flue gas velocity needs to be 30 feet or 35 feet. So 80% of the stack damper has to be closed in order for the damper to control the draft effectively. Otherwise, it's almost meaningless. If whether it is fully open or fully closed, it will not work. So stack damper was grossly oversized. We need to close almost 80% of the damper area to be effective. And that's why we have developed a smart damper. And smart damper is basically very, very simple concept. And it has, instead of one actuator, we have two actuators. And by having two actuators, we can basically change the CV of a control valve or CV of the stack damper. We can change it. And it improves the safety, reliability, and efficiency of fire heater. You can get better control of excess O2 and draft. So what we are thinking is it pays out within 6 months. That's how fast the payback is. I mean, it can be, you can take the existing damper and all we need is change the linkage and change the actuator, add an actuator. It's that simple. So think about it. If you're having draft control issues, this damper can definitely help you. I have a few minutes. Let's quickly go through API 560. We wanted to give it more time, maybe a few more minutes, but I'm running about 5 minutes late. So API 560 is a standard for design guidelines of fired heaters. We were going to talk about the changes which have taken place in the last addendum, which came out in May 2021. The fifth edition was issued in February of 2016. It's a standard for fire heaters for refinery service. It's a very good document. If you have not read it, you should read it. I found out that most of you have not read it. You can get a copy of API 560 and read it. It will give you a lot of information if you are in the purchasing, what are the mechanical requirements, what are the minimum requirements for design, etc., for shipment, erection. So it's a very good document. It will add to your knowledge. What it does not cover is the process design, and that's where the things become ugly or things become. It leaves the process design to the fire heater vendor and to the engineering companies, and that's I think more needs to be added in the API 560 to strengthen the process portion of the heater design. API 560, has been there. This team has been working for almost 50 years, meets twice a year. Now, what you want to see is representation of end users. In 70, it used to be in 1980s, it used to be 75%. Today, it is less than 15%. So the committee is kind of dominated by vendors, and when you have vendors dominating the committee, instead of strengthening the specifications, the specifications getting start diluted. That's what kind of happens in these things. And they are still doing very good work. They issue new standards every 5 to 7 years. So the first edition came out in 86 and the last edition came out in 2016. Very good edition. It's such a good edition, a document that you can buy a good heater with a process data sheet and API 560 specs. And API 560 is very well respected throughout the industry. So one of the things which API has added in this is this floor firing density, especially for low NOx burners. They have come out with a new guideline that the floor density should be less than 300,000 BTUs per hour per foot square. This is a really good specification they have added. I still have another quiz. So what happens if the amount of excess air is reduced in the fired heater or excess O2 is reduced? So anytime you reduce O2, average radiant heat flux goes up and efficiency goes up. I think those are both correct answers. However, when you reduce excess O2, the flame size also goes up. You have to remember that, and that can sometimes be a problem. So what is the percentage excess air in your fired heaters? Excess O2 or excess air, generally it ranges between 10 to 25. So 15% or 3% O2 is a very good answer. That's where most of the people try to operate their fire heaters, and that's what we kind of recommend. Now, what has happened in the latest edition of API, they have reduced the excess air from 20% to 15%, 25% to 20%, 5% reduction in the excess O2 or excess air. In my mind, it is not a very good design. It's basically to the earlier specification was more conservative, but this is what they have changed. I just want to make you aware of this. This is, I think, you have to see which heater. I think we talked about in the beginning, which heater is the best design, a better design, a fired heater, H by D ratio. Thank you very much. I think that's what I want you to have. H by D of 1.75 in all your future heaters. If you go with 1.75, your heaters will be very, very reliable. And that is what has happened in API. What API has done is instead of reducing the limit, they have increased the limit from 2.75, they have gone to 3. The tube length, they have gone from 60 to 70 feet. So it's kind of going in the other direction, which is going to hurt and we will not be able to have uniform heat transfer in the fired heater. They have done the same thing for the cabin heaters. Instead, we were limited to 2.75. Now they have gone up to 4. So they are saying height to width ratio can go up to 4. I don't know if it's a good this thing, but to me it appears that this is kind of diluting the specifications, making heater design tight, and maybe leading to more problems. So, well, thank you very much for giving me a patient hearing. I hope you liked what I had to tell you. So, did this webinar match your goals? Were you able to, I know you spent an hour and a half with me. Was it really useful? Or, well, thank you. At least most of you liked it. Was I able to, were you able to hear me clearly? Was my diction okay? Does it need improvement? Let me know honestly. Thank you. I try to keep it as simple as possible. And I think last is about my performance. How did I do? I got some feedback from my team also. So thank you all very much. If you have any questions, please send us an email. Please send us a message. We look forward to working with you on your next heater project, or if you have a heater where you are having issues, give us a call and we'll like to help you out. Thank you very much. We will do another session on ethylene crackers next month, and then it will be followed by a session on steam methane reformers, and then again we come back to our refined heater. So we are planning to do a session once every month. Please spread the word. Let us spread the knowledge, and hopefully it will all help you out. Guys, thank you very much. I do have this. Normally there should not have been any score, but thank you all.